So it'll be a lot of fun. Trying to think if there's anything else I should cover. I don't think so. We'll go ahead and jump in then. Talking through kind of some introductory stuff. So first of all, as we're thinking, if you want to pull up the slides on your laptop, there's a YouTube URL in the syllabus. You can pull that up as a live stream on YouTube. I might actually change that because there's like a 10-second delay, and that's really annoying to deal with. So I might do something different. I'll let you know if I do, because I know there's a lot of seats that you can't really see the screen from. So sorry about that. If you want to pull it up on your own computer, you can follow me. I also post the slides on Canvas after class, so you can download them there too if you want to review anything that you missed. So the first thing, thinking about web development, we have to consider how people are accessing our websites. So obviously web browsers are the main way that people access websites. We've got Chrome, Safari, Firefox, and Internet Explorer. They're all a little bit different. They each kind of have their own quirks that we have to keep in mind. We also have mobile devices. So that's becoming a very large segment of mobile traffic, probably about half and half on average now. Between all web traffic. Mobile devices present their own unique challenges. They have different screen sizes. Every mobile device is a little bit different. Pixel density, stuff like that. They also have different interaction behavior. Instead of a scroll wheel, you scroll with your finger, and that behaves a little bit differently. You can't hover on a mobile device like you can with a mouse. Also, things like even the orientation, portrait and landscape, things change a little bit. So mobile devices have introduced quite a bit of a challenge for web development because we have to be able to take into account a lot of different scenarios with the mobile device. Plus tablets, a little different. So one of the things that we'll talk about is responsive web design, where our websites can handle incrementally different, sizes of pages and still look good, because there's all kinds of sizes out there between, a computer or a phone that's in portrait mode that's pretty skinny, to landscape mode, to a tablet, to a full like a laptop screen. Those are lots of different aspect ratios and lots of different sizes we're having to deal with, and we have to make sure our site looks good on all of those. One thing we have to keep in mind. Another thing we'll talk about a lot in this class is screen readers. So screen readers are software used by people with visual impairments or other disabilities that need the contents of a screen read aloud to them. So again, it'll read aloud the contents of a computer screen, not just websites. The Americans with Disabilities Act, or the ADA, provides some guidelines for designing websites to be used with screen readers. And in fact, a lot of times if you're working for a larger company or any sort of government organization, including most educational institutions, they require you to follow these ADA guidelines. And there's some laws that are going into effect here in the next year or two, in fact, that really require pretty strict adherence to these guidelines. So it's something we really have to keep in mind. There's unique challenges when your content is going to be read aloud. You have to make sure your HTML is formatted correctly. You have to make sure any images also have text content that go along with them if they're important. So that's a pretty big thing we'll talk about throughout the class as we talk about different HTML features. Wait for the delay. I'm trying to remember to hit it and then talk about it. It's going to take a minute. So this is kind of a breakdown. If you go to analytics.usa.gov, they provide you with analytics information for all federal, U.S. federal websites, which is really fascinating. It's really fun to look at. This is from 2017, from around this time last year. And so you can see the device breakdown. So it's about 55% desktop, 39% mobile, and about 6% tablet. I think now someone checked for me last class, it's at like 42% mobile for 2018. So it's grown 2% in the last year. That's likely going to keep growing a couple percentage points every year, if I had to guess. So again, less and less people are using computers, traditional computers. A lot more people are using mobile devices for most of their web browsing. So you can also see the breakdown of browsers. So obviously Chrome is the most popular, followed by Safari and IE. Firefox, you can even see the version breakdown of IE. Edge is like the new version of IE, so they changed their naming from numbering to Edge. So that's the very newest one. You can also see the operating system breakdown. So Windows, interestingly, there's more iOS users than there are Mac users. So that's kind of interesting to see. So the whole point of looking at this is knowing that there's a wide variety of devices that we have to be able to present our websites to, including different combinations. You can have Chrome on Windows and Chrome on Mac, and they might be slightly different because Windows and Mac might render screens a little bit differently. So we've got a wide variety of devices we have to keep in mind. Browsers can behave slightly different. They all, in theory, follow the specifications of HTML and of CSS, and they should all be the same. But the specifications aren't perfect. There's room for interpretation when you're looking at the specifications, and each browser does it a little bit differently. They all have, Chrome and Safari share the same rendering engine, but IE and Firefox each have their own rendering engine. So the software that actually draws the HTML on the page and determines how to size things, completely different. So there's little quirks to how they do things that we have to keep in mind. So we'll talk about how we actually do that as we go through the class. This next slide is from Google Analytics on a website that I've worked on for just a local church. So they have a little bit different demographics in their breakdown. I found this really interesting when I was looking at it. Their mobile is quite a bit higher. They have more mobile than desktop. It's almost reversed. It's a little bit more extreme than that even. They have 55% on mobile and only 37% on desktop. And so I thought a lot about that. I was like, why is there so different than government websites? And I think there's a couple reasons. For one, local companies and local organizations probably have a lot more mobile interaction because people are just pulling up their information on their phone to get information about what's going on or what their hours are or where they're located, things like that. So a lot more kind of quick searches. Also, if you're going to the IRS website to pay your taxes, you're probably not going to do that on your phone, I would guess. So a lot of official government interactions you're probably going to pull out your laptop for because there's more information you're going to have to type in. So even though, the federal analytics shows, more desktop, we have to keep in mind there's some websites where we're going to see significantly higher mobile usage. So in the case of this website, I put a lot of work into the mobile view because that was a big deal. Google Analytics is a great tool. You can add it to any website that you've developed. There's just a little JavaScript tag that you include, and then they let you see all this breakdown. It even goes further. You can see age demographics. You can see location demographics. You can really get into the weeds on the demographics of your visitors. So it's really, really useful. You can even track goals and different interactions and stuff like that. If you have questions, by the way, feel free to show up your hand or interrupt me, and I will answer it. So the internet works on a client-server model. We're going to talk a little bit about web servers and where we put our websites to make them accessible. So clients are the browsers and the computers that are accessing a resource over the internet. So when we talk about front end and back end, front end is the same as the client. So it's the part that the user sees. It's the user coming to interact with the web page. Servers are the computers that host the resource. They're just computers. They have all the same hardware as your laptop, but it's specially configured and designed to be able to handle large amounts of traffic, to be really easily maintained, to stay cool, and they're usually really powerful computers as well. But when we talk about backend, that's the server side of things. So that's the server that's processing requests and returning the web page. So front end development and back end development is kind of a buzzword that's developed over the last few years. I think it's kind of most jobs I've had handled both. Most of the time we're dealing with the front end, we're dealing with the HTML and CSS, but we're also working on the back end. Some jobs are a little more siloed. Sometimes you'll only work on the front end, sometimes you'll only work on the back end, but that's what those terms mean. There's software installed on web servers that actually serve the web pages. So Apache is a really common one. Nginx is also becoming more popular. That's the software that actually processes a request and determines how to respond, determines what files to look up, or if it needs to run PHP, or if it needs to run Java, or whatever it needs to do. That's the software installed on the servers that handle those. Servers can also be any operating system, so Windows, Mac, and Linux all have server variants, so you can install Windows Server or Mac Server. Linux is the most popular, though, mostly because it's free, it's low cost, and it's pretty easy for remote management, so you can log in remotely and handle everything in the command line, which is typically how you handle things a little bit easier. So then web hosting companies will run large specialized servers for many, many websites. So they'll have racks and racks of servers that handle tons of websites on them, and they kind of manage everything for you. So if you want to run your own website, like I have a server at home that's just one little tiny server, and it runs one website, but like I don't run anything important on it because say the hard drive failed. Okay, I have to go buy a hard drive. My website's going to be down for like 2 days while Amazon ships me a new hard drive. I have to install it. I have to transfer files. It's really complicated to like maintain that hardware. Plus, it uses a lot of electricity. It runs my power bill up a little bit. It generates heat. That room that it's in is usually a little toastier. So web hosting companies take care of all these problems. One, they have full-time staff that manages things. They're really good at swapping out hardware if it goes down. They have specialized cooling and do water cooling and have giant fans and all this. So they kind of, do a really good job at managing those web servers. So it's not usually practical. Most companies are moving away from managing their own servers. And they're kind of outsourcing it to hosting companies. Or, here's a picture of a server. Just for fun, this is what mini servers looks like. So each one of these little, horizontal things is a server and a rack. This is, so again, they're just computers. This next image shows the internals of one. So this is the inside, you can see the one unit of the server here. If you've ever built a computer or opened up the side of your computer, you probably recognize there's the hard drive, there's the CD drive, but you can even see the RAM here. So again, it's just the same thing that's in a normal computer. It's just specialized in a different format, and typically even a little bit more robustly built to be a web server. So for a website to be publicly accessible, it needs to be hosted on a publicly accessible server. Again, typically provided by a web hosting company. So like my server at home, it is publicly accessible because I've set up my router to allow, the outside to come in and to read it. So I can access it remotely. But typically, if you run a website on your laptop, unless you've set it up to be publicly accessible, I can't access your laptop over the internet, so I'm not going to be able to access the website on your laptop over the internet. So as I kind of mentioned before, web hosting is kind of an economy of scale, right? So the more you have and the bigger you are, the easier it is to manage things. So large data centers can manage thousands of servers. They can do cooling really well. They can have staff. They can even worry about physical security. So, if you have a web server that's going to host private, sensitive data like credit card information, you have to lock everything down. You have to make sure access to, those servers is controlled, because if someone was able to get into your server room and plug in a USB thumb drive and copy some files over, they could get some important stuff from that server. So physical security is a big deal. So again, it's much easily managed, in a centralized environment. Virtualization, by the way, anything that's in bold is maybe something you want to keep in mind. It might be covered on a quiz. Other than that, don't worry about memorizing too much, stuff from the slides unless you see something in bold. So virtualization is a software technology that allows servers to run many virtual machines. So it sort of allows you to abstract a server. So you can have a server with hardware, and then you can run many virtual servers that each run in their own kind of isolated environment on top of that server. And they have access to a portion of the host machine's resources. So, say you have a server with, 4 CPU, like a quad-core CPU, and, 32 gigabytes of RAM and a 500, or like a 10 terabyte hard drive or something. You can create virtual servers that have access to 1 CPU core and 8 gigabytes of RAM and 500 gigs of data, something like that. And you could run however many of those you can fit within your resources. You can also pool virtual servers across servers. So you can use virtualization to create a virtual server that has access to the resources of multiple servers. So like Amazon will do this. You can access more than just one server's worth of resources. So most web hosting companies operate this way. They create this, kind of isolated environment for you that has access to some resources, but it's only a portion of what the underlying hardware is. So whenever you see like VPS, that stands for Virtual Private Server. That's a common term used for this. Hypervisor is the actual software that manages the virtual machines. So stuff like VMware or Zen are common virtualization things. One big downside is it introduces some security risk, and that's some of the largest security issues we faced in web development over the last few years have been related to virtualization. Because it's the only thing keeping you from, again, if you're one of 10, virtual machines on some hardware, if you're able to break out of the virtualization and access other data on that hardware, that's a pretty big deal. So there's been security vulnerabilities in these hypervisors that have allowed you to, see other customers' data or access, other stuff hosted on the same hardware as you are. So that's some downside to virtualization. It's not there's some risks involved, and we've seen that a lot. Some of the bigger hacks have been related to that. So related to virtualization is cloud hosting. So cloud hosting, the term cloud really just means like large. That there's big servers, a large pool of resources that's virtually unlimited. So when you think of like Dropbox or something like that, which is a cloud service, it just means that when you create a Dropbox account, no one's going and plugging in a hard drive saying, okay, here's Craig's Dropbox account. It's all pooled together, and it's pretty much unlimited. You can upload however much stuff you want, and Dropbox has hundreds of thousands of hard drives plugged into their servers, and they can allocate it as needed by demand. So that's all the cloud really refers to, is this kind of global pool of resources that's available over the internet. So cloud providers usually provide some really nice features that provide scaling, because again, you can use however much you want. If you need more storage, all you have to do is upload the files or provision it. You don't have to worry about buying hard drives or anything. They provide some really useful management tools, other services like DNS settings. You can do your networking all in the cloud, databases, stuff like that. So some common cloud hosting providers are like Amazon Web Services, Microsoft Azure, Google Cloud. I think all three of these provide you with some free stuff. I know Amazon lets you run their like lowest tier of server for like a year for free. So if you want to, mess around with web hosting, or you want to kind of learn how to manage servers, Amazon's a really great place to go, because you can do it for free for up to a year. And then I think you can just create different accounts and still get the free. Then Google Cloud also has a free tier. At the same time, one of the big pros for cloud services is you typically pay for what you use. So if for some reason you wanted to try something out on a really beefy server, you could spin up a server with a lot of resources, and you'll only pay for however long that server is active. So I did this recently. It was a project we were doing at work for fun, that we were doing some machine learning. And so machine learning is really resource intensive. It's also really more efficient on GPUs. Amazon Web Services actually provides you one of the options for their virtualized servers is servers that have GPUs attached to them. And they have very large ones. So we would spin up like a virtual server that had like 20 GPUs attached to it. And we would run a machine learning task that took like 2 minutes, and then we would shut the server down. So we would pay maybe like a couple of dollars for a few minutes of a massive server. So that's a really nice feature that you can't really recreate on your own by buying hardware. You couldn't go buy tens of thousands of dollars worth of hardware and set it up just to run one task. But with AWS, you can, and it's really cheap. So that's a really big benefit of cloud providers. It's also usually a little bit cheaper in the long run. I think even still, people are getting worried that at some point they're going to start raising their prices and it may become more expensive. But for now, it's generally cheaper to centralize all of that management and just kind of let AWS do the hard work for you, and then you just use their platform. It's also easier. Again, I spun up a massive server with. It took like 10 seconds to create the server, and it was available to me. Way easier than managing on your own. Also, usually automatically managed. So again, they do all the hardware configuration. They do a lot of the hard work for you. Again, there are some cons. We've got some security risk. Again, you kind of have to trust them when they tell you that you're in an isolated environment that no one else can access. You're like, okay, but there is some trust required there because there's some security risk. A lot of these now, AWS, for instance, lets you kind of supposedly run on your own private hardware, so you can pay extra and have your own dedicated servers within AWS, but that gets a lot more expensive. But really, security-conscious companies will do that. They'll pay extra, especially once you're paying tens of thousands of dollars a month for your hosting. Amazon will kind of you're already using several servers worth of hardware anyway, so they'll isolate that for you. You also have some less control when you're using cloud providers. If you need really specialized hardware, or if you really care about specific aspects of the way it's managed, you don't really have control of that. You're really restricted to the options that they give you. So if you wanted to build some custom server that had a certain configuration, you can't really do that. You're restricted to what they give you. You also have vendor lock-in, which is a big deal. If you go with AWS and your service grows and you really buy into AWS's services and you use them and rely on them very heavily, it's kind of difficult to move away from them. And a lot of companies are finding this out recently, especially if it gets more expensive than you'd like, or you decide you'd like to bring it all in-house. There's some vendor lock-in involved. So something to keep in mind before you get too far. Any questions about anything so far? Okay. Splash water on myself. I really suggest, especially if you're interested in, web development as a career, to, sign up for a free AWS or Google Cloud account and find some tutorial. If you just Google how to host a website in AWS or how to host a website on Google Cloud, you can find tutorials. Just walk through the tutorials and come to understand the steps involved, because you'll, probably have to install Apache or some sort of, web server software. You'll have to go through some steps of getting your files up there and figure out how to upload to it and how to manage things. And so it's really useful to kind of understand how that architecture works a little bit. Okay, so how websites work. So websites are accessed by a URL, which is called stands for Uniform Resource Locator. The URL consists of a few different parts. So the first part is the protocol or the scheme, which is the HTTP:// or HTTPS for secure connections. There's a few other protocols. You might be familiar with FTP, which is like a file transfer protocol, or there's a few others. Even like Tor, if you've ever done like BitTorrent, that's technically a protocol that's not using HTTP. So HTTP stands for Hypertext Transfer Protocol, so you're transferring hypertext, which is just HTML. And HTTPS is for HTTP Secure. All data is encrypted between your browser and the server in HTTPS. And HTTPS should almost always be used. We'll talk about that a little bit more in a little bit. So after the protocol is the domain. So that's the main address of the website you're accessing, so such as google.com. It may include a subdomain like www, so if there's anything before like www. Or maybe like docs.google.com or something like that, whatever is before that dot is the subdomain. You can even have multiple subdomains as well. So you could have new.docs.google.com or something like that. You can have as many subdomains as it's configured to allow. The .com part is called the top level domain, or TLD. So it can be many options. Up until a few years ago, all we really had were .com or .net or .edu, like .gov. But a few years ago, they opened it up. TLDs are managed by an organization called ICANN. So they determine, what these top level domains are and who's allowed to use them. But they've opened it up. There's thousands of options now. So like .io is really popular. Like .website is one. Like there's literally thousands of options now for those top level domains. So you can really kind of tailor it to your website. Um, and that's managed by the your registrar. So when you register for a domain, you choose what top level domain you want. So after the domain is the path and or the file name, so /folder and then /some file. It doesn't always include a file extension like HTML. HTML is the default, so if you just go to like google.com/search with no file extension, it's going to be HTML. But sometimes you will see a file extension on there, especially if you're just accessing a HTML file that's not generated by some sort of programming language, or if you're accessing an image or a PDF file or something like that, you'll see the file name. If you have a domain with no path, it's called the domain root. So if it's just google.com, you would call that the root of the domain. Something to be aware of. This next slide is a graphic that illustrates the URL anatomy. So again, first we've got the scheme, followed by the subdomain and the domain, then the top level domain. You also can have a port sometimes. So if you ever work with like Node.js locally, usually it uses port 3000, so that's how you indicate the port. But 80 is the default for web traffic, or 443 if it's secure, so those ports aren't included, just because the browser knows how to handle it. So then you've got the path, and then you can also have a query string. We'll talk about that a little bit later maybe, but that's if you're providing some data along with your URL, like maybe if you're getting something with a specific ID, you can pass that ID through the query string. Then we also have a fragment identifier, so this will jump to a specific location on your web page. Again, we'll talk about that a little bit more when we get into HTML. Any questions on this? All right. So IP addresses. So your computer needs the IP address of a server that contains the website in order to download it. So this is what IP addresses look like. This is IPv4, which is kind of what you probably are most familiar with. As you can tell, there's not that many possible combinations, and every single device that's connected to the internet has an IP address, at least through a specific like, for instance, all of our devices here probably have the same IP address internet facing, because WashU probably has a handful of IP addresses for, that face the internet. All of your devices at home probably share one IP address. But generally, especially with mobile phones now, if you're on your phone and it's just on your LTE or something, it has its own IP address. So because we have so many mobile phones now over the last 5 years, it's exploded. We have Internet of Things devices now, so little devices everywhere that have internet connectivity. If your doorbell has the internet on it, it's got an IP address. So we're actually running out of these IPv4 addresses. I don't know what the official status is, if we are officially out of them or not yet, but there's only so many, as you can tell. So a few years ago, they finalized a specification for a new format of IP addresses that's hex encoded. So this is called IPv6. So you start to see this a lot more now. It's becoming a lot more common. And in the next few years, probably you'll start to see everything kind of switch to using IPv6 more and more, because it's hex encoded. There's billions of different permutations available, so it's going to be a lot more flexible. But it is a little bit harder to read and understand because it's hex encoded. There's a lot of cool features with IPv6 too. If you're interested in kind of networking stuff, you should read up on IPv6, because they can be consolidated and shortened, and there's different ways to do masking. It's kind of an interesting format. So, but you don't have to memorize these for the class or anything. But after you've typed in a web URL like google.com, your browser first has to query what's called a domain name system, or a DNS server, which knows the IP for that domain. So it's sort of like an address book that correlates domains with the IP address of the server that hosts the website for that domain. So google.com exists on a server somewhere, probably exists on lots of servers, but there is one IP address that will take you to google.com. Probably an IP address to a load balancer that then redirects it to a specific server. But the domain name system is what's responsible for telling your browser what the IP address that it needs to make the request to. DNS servers are typically, run by your internet service provider, so Charter or whatever will run domain name servers. Large companies like Google and Microsoft also have their own. Typically DNS servers all sync up. So all around the world, there's probably hundreds of thousands of domain name servers, and they sync up over time. They share information with each other. So like when you create a website, if you buy a domain and you set the IP address in the DNS settings for that domain, it may take like anywhere from a couple minutes to a couple hours for everyone around the world to be able to find your website via that domain, because we call it propagation. So that DNS information, that mapping of domain to IP, takes a little while to propagate to all the servers because they only refresh every so often. So it takes a while for that information to make its way around. So it's something to keep in mind if you change the IP address of your domain. Keep in mind it may be a few hours before everyone will reliably get to the same place. Your browser also will cache DNS entries. So if you've gone to google.com once, it's made a request, it says, okay, I know google.com is this IP. Your browser or your computer saves that. It maintains a local database of those, so it doesn't have to make a DNS lookup every time. But it will refresh it every once in a while, as well as if you go to a new website, it may have to look it up. So here's a handy graphic of what that looks like. So when you put in some website in your browser, you first query the DNS server. You say, what's the IP of foobar.com? DNS server responds with the IP address. So now you can make the request directly to the web server with your URL. The web server will process and then return the response, the resource that you requested. Questions about DNS? Okay. So once your computer knows the IP address of the server that it's going to get the website from, it makes a request to the server for the URL. And at that point, HTTP, which is Hypertext Transfer Protocol, is the protocol that's used by the client and the server to talk to each other. So it's kind of like a shared language that they're able to use to make the connection and to transfer data back and forth. So there's multiple layers under HTTP. It's using TCP or UDP, at a networking level. It kind of gets deeper and lower level from there, but HTTP is kind of the top application layer protocol that's being used. So we'll talk about some details of how HTTP works. Typically the browser handles all the HTTP for you. All you have to do is type in, the URL and the thing and hit enter, and it handles all of this stuff for you. But especially as we get into JavaScript and we start interacting with APIs and we're doing AJAX and data fetching and stuff like that, we're going to have to deal with some of these details about how HTTP works. So we need to be pretty familiar with kind of some of the lower level details. So the first part of HTTP is the request. So that's your client sending the request out to the server. And those requests contain several parts. We've talked about the URL. We then have the request method, or sometimes called the verb. So it's the type of request being made. So we're saying this is, here's the URL, and then there's a type of the request. Get and post are the two most common. It's what we'll deal with in this class. So get is the most basic request of just requesting a resource. So it literally is saying get. So here's a URL. I want to get that resource. I want to fetch it. And it should only retrieve data. It's not making any changes. The server shouldn't, change anything due to a GET request. It's what we call idempotent, where it doesn't make any changes. It just makes a request, and the server returns a response. Nothing changes. So if you're using a GET request and to share data with the server, something like that, you shouldn't be doing that. You should only be using it for requests. We do submit data using post requests. So it will submit data to the server. So it's used for form submissions or writing a post on Facebook or sending a tweet. That's all where you're sending data to the server and you're requesting the data or the server to do something with that data. It's usually storing it somewhere. It may post it somewhere else for other people. but it's where you're sending information, the data. Those should all use post requests. There's a few other, request methods. There's head and put. Head just gets the headers in the response. It doesn't get a response body. So it's a good way to check and see if a website's working or get, some options. Put is where you would take like a fully formed data object and you're telling the server, here's a data object. I want you to store it. So sometimes we'll see put, whereas post can be some fragment of data or something like that. So here's kind of an example of, how we use HTTP verbs. Delete's also one we'll talk about here, but we won't really use it in class. But so say, we're accessing some sort of store. We might make a GET request to /store/inventory. So we're saying, I want to see the inventory, return the response to the inventory. It's not making any changes. The store's not, saving any data. It's just going to return with the inventory. Then we might, say we see an item we like. There's an order button next to that item. We click the order button. Maybe we have to put in our name and our credit card details. Click submit on the order. Then we'd make a post request to like /store/order. So that post would include the details of our order. So like what items we're ordering, how we're paying, what the address is, that kind of thing. So that's where we're sending information, the data, or we're sending data to the server. The server is going to have to do something with that data, right? Like when we submit an order, the server probably saves it, probably processes our credit card, it probably triggers some sort of fulfillment, it's going to start packaging it. Something's going to happen as a result of that post request, right? So that's where we're sending some information. Then we could maybe do a GET for a specific order. So we could say GET /store/order and then some order ID like 1234. So maybe we want to like look up the details of our order to see if it's shipped yet or something like that. Again, we're making a GET request, so nothing's changing. We're not deleting the order. We're not editing it. All we're saying is we're fetching the information about that order with our GET request. But then maybe we can make a delete, which again is just another verb. It's less common, but it's in this example where we use the delete request method on the same exact URL that our GET is, right? So it's the same order ID, store/order/1234, but because we're making a delete request, the server knows that we want to delete that order. So it's the same exact URL, but it's a different HTTP request method that indicates the server should do something different. So it's going to actually delete it. We could maybe do a post to that order ID if we wanted to change it. We could do a post with a new address or something like that. So again, those verbs can play a big role in telling the server what to do, telling the server what we're wanting to do at that URL. So the next thing to talk about is the HTTP request headers. So headers are sent along with our request, and they contain kind of some meta information about our request. So this is not an exhaustive list. This is just a few examples. You don't have to memorize all these or anything. But it's important, typically your browser handles all these request headers. You don't, adjust them in your browser. But when we're dealing with JavaScript and making AJAX requests, we might need to change some of these headers. So they're important to be somewhat familiar with, that they at least exist and what kinds of things can be included in the headers. So like host is where we include the domain name of where the request is being sent. So if we, make a GET request to google.com/search/ something we're searching for, the host would include just google.com. Accept is the type of media that we're requesting. So what types of response we accept. That's why it's named accept. So typically it's going to be like text/HTML, which is saying like, I'm making this request and I would like you to give me HTML back. Or I will accept HTML in response. Sometimes if you're wanting to download a file, it might be different. It might be like a JPEG or something like that. So you're saying, here's a request, I will accept JPEG data back. Accept language is saying what type of language you'll accept back. So typically it's going to be English, but that's where you're identifying what language your browser uses. And so the server knows what language to respond in. Cookies are really important. So cookies are data that the server has previously sent to us, and it's told the browser to save and then include with all future requests. So for instance, when you log into a website, once you've successfully logged in with your username and your password, the server will send a cookie to the browser that's some sort of token that verifies that you're logged in. It has your user information involved. It's basically like a secure cookie that has, it's like your login token. So then every request that you send, when you go to facebook.com and you log in, if you click on another Facebook page, you don't have to log in again, and that's because of the cookies. There's a cookie that has a secure token that gets sent to every future request. So Facebook can see that cookie in your header, and they know, okay, they're logged in, this is the user, we know that we can send them the data specific to that user. So there's all kinds of things cookies are used for, user session IDs, security tokens, so if you've logged in. Tracking information is used, so a lot of websites will track you. Google knows about other websites you go to because of your cookies. Other websites will inject Google cookies that they can track. So it gets kind of crazy. That's why you might have noticed like a few months ago, I think it was now, like every website ever had a big message about cookies. It's because the EU changed some of their laws regarding cookies because it's kind of a big deal with privacy, right? Like if you go to some, blog, they might know what your Facebook user ID is, and they might be able to tailor their ads to you based on your Facebook information, which is kind of crazy. And if it's not something that you've opted into, or if it's not something you're aware of, it can be kind of creepy when you start seeing ads related to, something that you like on Facebook. If you like some page and you start seeing ads for it on another website, you're like, wait, how did that happen? It's because of cookies. It's because those, that website and Facebook have agreed to share cookies so that they can relate, your user data. So that's the EU kind of cracked down on that, and they said, yeah, that's kind of creepy. You at least need to tell people that you're doing that so they can opt out of it, or they can at least know not to visit your website because you do these creepy things. So that's why everyone kind of scrambled. Even at my work, they're like the laws changed, and then they went into effect, and everyone was like, oh crap, we have to do the steps required to comply with these laws, especially if you do business in the EU at all. So that's where all those cookie notices came from. It's basically just informing you that they use cookies and telling you how to opt out if you wanted to. So cookies are a big deal, and those come through the request headers. That's how the website sets the cookies and tells your browser what cookies to start saving and to include. This is the request header. So these are cookies that have already been set, and you're sending them along with your request. They get sent with every request to that domain. User agent is a string of information about the client. So what kind of browser you're using, usually even what version of browser, what operating system, what kind of computer you have, sometimes even what kind of screen, sometimes even like what kinds of extensions you have installed, or what capabilities your computer has. We've actually run into some privacy issues with user agents even because they're pretty uniquely identifiable. There's a website, I can't remember what it's called. It's like Browser Leaks or something like that, that'll show you all the information your browser's sending about your computer. And if you correlate, like a specific browser version and a specific operating system version and, a specific extension version or something, you can kind of uniquely identify someone by that. So there's some privacy tools now that will change your user agent in the headers to either wipe it out or make it really generic. I use a custom one so that when I'm, debugging stuff at work, in my logs, I can see my own custom user agent. Like in my user agent, there's an extension for Firefox or Chrome that lets you change your user agent. So I've made mine like Craig's computer. So in my logs, I can search for Craig's computer, and I can see all the requests that my computer has made because that user agent shows up. Of course, every other website now knows that it's Craig's computer. They know it's me, but that's all right. Content type we use with post and put requests where we're sending data, and it identifies the type of content we're sending in the request. So often it's like, JSON or URL encoded data, something like that. So next is the HTTP request body, which is only sent with post and put requests. Again, GET doesn't include any data, so GET doesn't have a body. All it is a request. But post and put requests, we're sending something to the server, so we have to include whatever data it is that we'd like to send along. It can be in a variety of formats. application slash form URL encoded is often used for form data. So if you have a form on your website, when you click submit, it's probably sending a post request with that type of data with all of your form submission details. We can use JSON or plain text even. Those are all options. Again, we won't really have to worry. Well, we'll have to worry about these a little bit when we're doing AJAX and we're, sending information to server via JavaScript a little bit later on in the class. So after the server has received and processed your request, so usually they have to, look up the page you're requesting, or if it's like a Java or a PHP app like WordPress or something, they're doing some, processing, running their PHP scripts to look up whatever you've requested. Then the server responds with an HTTP response, which contains several elements, the first of which is the HTTP response code. So it's a numeric value that indicates the status of your request. So 200 is successful. So if your request was good, the server found your resource and there are no errors, it'll reply with a 200 response saying everything worked out okay. There's also 301 or 302, which indicate that the resource is moved. So they'll say, hey, this is moved, you need to look somewhere else, the URL is changed. 404, which you might be familiar with, indicates that the resource wasn't found. So if you go to google.com/abcdefg whatever, that probably isn't a real page, so you're going to get a 404 response, and Google's going to say, yeah, I don't have a page called abcdefg. 500 is a little bit different. It indicates an internal server error. So if you go to google.com and you search for cats or whatever, and Google servers have an error, for whatever reason searching cats causes a bug in Google servers, it'll respond with a 500 error if things just break. So if you get 500 errors, typically it means there's a problem with the server itself. You may have caused that problem with the server with a bad request. I've run into this, in the application I work on for work, when we actually had some security testing a while back. So an outside security company started doing some automated testing of our website, trying to break into it. So they were just like sending all kinds of crazy requests, like making up URLs, and they hit a couple things that like something about the request broke our code. Like our code just didn't know how to handle that request, and it threw an error, so it sent a 500 response back. It's like that request caused a bug and something broke, and so here's an error. So typically 400 ones indicate a problem with the request, so your request is bad, something is wrong about the request, it doesn't exist. 500 typically indicates that something happened on the server and something broke. So again, there's more SAS codes than that. Typically 200 is good. There's even 100 level SAS codes, which are informational, but we don't really see those very often. 300 level are redirects of some sort. There's some new ones. There's like 307 and 308, which are different types of redirects. Again, some of the times they're permanently, it's saying, hey, like this is actually moved, you need to change your bookmarks or whatever. Sometimes it's just temporary. It's like, hey, this is changed for a little while, but it will later be accessible. Again, 400 is an error in the client, and 500 is an error with the server. So in the same way that our request includes request headers, the response also includes headers that provide some meta information about the response that's being returned. So again, these are just examples. These aren't exhaustive. Some of these you'll see pretty much all the time. Sometimes you'll see them occasionally. So age can indicate the age of the content if it's being returned from a cache. So it may say, this is a cached version of the page and it's a day old, so keep that in mind. Expires is kind of similar, but it indicates how long the browser can cache the page. So whenever you go to a page, your browser usually will try and save a local copy of that page. So like if you go to washu.edu, your browser is going to save a copy of that page, so that the next time you go to it, it won't have to download the page again. It can just load it from its local copy. But the expires header tells the browser how long to save the page for. So the WashU website has a day expiration of the cache. So what they're saying is the content shouldn't change for a day, or if it does, like it's not urgent that you have an up-to-date copy, because the main WashU page doesn't change all that often. However, like Facebook doesn't have an expires header because Facebook never wants the browser to cache the page because you should see fresh content every time you go to Facebook. Something like a news, like CNN.com probably has like a 5-minute cache, or maybe even 1 minute, because they're like, hey, it's going to update pretty quickly and we want you to always have an up-to-date page. But maybe you've got a couple minutes, so subsequent requests can load the cached version. Content type will indicate the type of content being returned. It's usually going to be HTML. Content length tells you what the length in bytes, which is handy for like if you're downloading something. It'll tell you how big the file is, so that's how your browser knows about how long it's going to take to download, because the length is included in the header. The server header will indicate sometimes the type and version of the web server that's being used to respond to the request. So it might say Apache version 2.1 or whatever. We're actually finding there's some security reasons for the server not to tell you what version it is, because sometimes they find vulnerabilities in certain versions, and if they know that you're using that version, they say, okay, great, I can attack you using this method because that's a known vulnerability. So best security practice is to not include the server header in the responses. But you still see it from time to time. Set cookie is the server's way of delivering cookies to the browser for the browser to save. So if you see the set cookie header, it provides a key value pair that the browser will save, and then the browser will include in all future requests to that domain. Location as a header will be included with 300 level responses to provide the new location. So if the server responds and says it's at 302, the location is moved, it provides the new location for you. So usually your browser automatically will redirect. If your browser gets a 300 response, it says, okay, is there a location header? Okay, yeah, now we'll go to there. So you don't usually have to manually then go to that new location. Your browser just does it for you. Any questions about HTTP response headers? We won't really worry about generating these, but we may read some of these when we're dealing with APIs and doing stuff with JavaScript. So we've got the response status code. We've got the response headers that give some information about the response. And then we've got the response body, which contains the main data that was requested in the response. Again, it's typically HTML, but it can be an image or JSON data or some other type of file that we're downloading. If you want to read some more on HTTP, here's a couple of links that kind of go through things. Again, there's a lot more going on, sort of under the hood with the way web traffic works. There's networking stuff. There's a lot going on there. That's kind of a very broad overview. This is an example kind of just raw HTTP, kind of what it looks like. So this is done just in the command line using a tool called curl, which does GET requests for you. So if we do a curl on like mit.edu, we see first hostname was not found in DNS cache. So the computer doesn't have the DNS info for mit.edu saved. So it has to do a DNS lookup. It does the DNS lookup, and then it says trying at this IP address. So this is the IP address for mit.edu. So then it says connected to the IP on port 80, which is the standard. It's just HTTP, it's not HTTPS, so it's going to be on port 80. So then the client starts talking HTTP. You can see when the arrow points this way, it's the client sending out, and when the arrow points the other way, it's the server returning, reading the response. So this is our HTTP response, or request here in red. So first, we're telling the type of response, which is GET. This is the URL, or the location, which is just the root, so it's just / meaning just the root of the domain. And we have to tell it what version of HTTP we're using. 1.1 is kind of the standard right now, sort of slowly being replaced by HTTP 2, which is a pretty new protocol that has some changes. It's got a lot better security. So you may see HTTP 2 from time to time. Again, the browser kind of handles all that for you. We then see the user agent header. So these three are headers. So the user agent is curl, which is the software we're using. If we're using Chrome, it would say Google Chrome version, 80 or whatever it is they're on. But this says curl, and it has our curl version that we're sending. The host is the domain that we're making the request to. So again, between the host and the URL here, that's our full URL. So mit.edu and then the path, which is just root. If we were searching like mit.edu/schedule, here it would say /schedule. So those two things combined make up the full URL. Then we have the accept header, and this you can't really tell here on the screen, but it's */*, which just means anything. It's saying I'll accept any type of response that you give me, so it doesn't matter what you return with. So then we see the HTTP response. So again, it identifies that it's HTTP 1.1, returns with a 200 status code, and usually it'll give you some short, if it's a 200 level, it'll say OK, meaning it was successful. If it's a 300, it'll say 300 redirect or 500 error or something like that. Then it has the server header. There's two server headers here. This one has to do with SSL, so it tells us we're using Apache 1.3. So again, if I were a hacker, this gives me some good information about the server I'm trying to hack into, because I know exactly what version it is, so I can look up, vulnerabilities related to that version of Apache. Tells me I'm on Unix. It tells me the OpenSSL version, which is what does the HTTP security stuff. It tells me when the page was last modified. This E tag is just kind of an identifier. It tells me the content type, which is text HTML, so it's returning HTML. It tells me the date, the current date. It tells me the content length in bytes, so this is how big our page is, how much data it's going to give us. There's also this connection keep alive thing. And then below that would be our HTML that's actually responded in the body. So here you can see what the headers look like. Any questions about HTTP? Again, we won't be doing this kind of stuff in the class. We're mostly trusting the browser to handle all the HTTP stuff for us. It's just really good to be familiar with. Especially if you're going to do any sort of professional web development, you need to be kind of familiar with these concepts so that you can debug things, you can figure out problems. And especially if you're using JavaScript, we'll have to manually set headers sometimes and manually read headers that come back from our responses. Yeah.
Where would we find that page in our computer?
Oh, if you have a Mac, curl is installed by default. So you can do like curl-v, which says verbose, and then some URL, and it'll process that request for you. You can see it. I'll show you an example here in a little bit too. Okay, so secure HTTP. So HTTPS is the aptly named secure version of HTTP, which encrypts all communication between the client and the server. So everything is cryptographically encrypted. HTTPS requests begin with HTTPS : / and they typically use port 443 instead of port 80. Again, you don't have to worry about that. It's stuff your browser handles for you. So without HTTPS, it's possible for outside parties to intercept and read or even modify the data being sent between the client and the server. So outside parties being anyone else who has access to read the network data. So without HTTPS, all of your requests and all of your response are just in plain text, and they're easily readable over the network. So it was around like 5 or 6 years ago, this really came to light because back then most websites didn't require you to use HTTPS even for logging in. Sometimes like their actual login page would use HTTPS, but then it would go back to regular HTTP once you were logged in. So there was actually a Chrome extension that somebody made 5 or 6 years ago that would sniff your Wi-Fi traffic. So if you're on public Wi-Fi that other people were connected to, and as long as there was no password on the Wi-Fi, then it was just all totally in the open. And you could sniff HTTP traffic from other people. And what it would do would pull authentication tokens from like Facebook or Twitter. So if someone had logged into Facebook, there's a cookie that's sent every time they go to facebook.com then that is an authentication token that proves what user they are. And in the Chrome extension, you would see all of these, Facebook users pop up and say, okay, here's Steve, he's on, your Wi-Fi and he's logged into Facebook, and you could click on it and it would steal that, it would just copy that session token, insert it into your own cookies, and you would be logged into Facebook now as Steve. So a pretty huge security vulnerability. You could be at Starbucks and you'd see everyone logged into Facebook and you just log in as them. So the extension got shut down in like 2 days because obviously it was a huge deal. But it made a big point, which is that like even once you're logged in, you should never be on regular HTTP. You should always be secure. Otherwise, anyone that can sniff your network traffic can steal sessions and log in as you and do all kinds of stuff. So it made a huge splash, and honestly, it was probably pretty instrumental in sites like Facebook and Google and Twitter now require HTTPS all the time. Even the WashU website requires you to be on HTTPS before you've even logged in. So it's really common now to only allow HTTPS connections. Otherwise, anyone can read. Even worse, people could modify it. You could intercept the traffic. You could modify, the HTML. You could insert some malicious JavaScript or something and install malware on the user's computer. You can do some really nasty things once you can, intercept that traffic. So HTTPS is a huge deal, and over the last few years, thankfully, it's become more and more common. It's a lot easier to get HTTPS certificates. So now most websites require HTTPS, even if they don't contain sensitive data. So again, if you go to washu.edu, you're not doing anything sensitive until you've logged in, but they still require HTTPS because someone could modify the contents or do something misleading. It's a pretty big deal. So you'll always know you're on HTTPS if it's green. Typically, most browsers make it green just as a way of reinforcing that you're on a secure site. They show a little lock there. If you click that lock, I'll click it here. It'll take a second to load, but you can actually see some of the information about the certificate. You can even, view certificate and see some details. Click like more information, and then view certificate like that. You can see, that this certificate is for anything.google.com. You can see that the organization is Google LLC. You can see it's issued by Google themselves, so Google has their own certificate authority, so you're kind of trusting Google that they're verifying Google, which is maybe not a great practice, but they're big enough now, I guess, we can trust them. We see that it expires in October 2018, so they're going to have to update their certificate pretty soon. Typically, when you buy a certificate, you want to get one that lasts as long as possible. So you can kind of see some details there. Out of these. So, just super brief overview of how HTTPS works. Before you are able to send data back and forth to the server, you do a handshake, what's called a HTTPS handshake, and you exchange keys. So you send your key to the server. There's more that goes on here. But then once you've done that, you can see the data, so you can enter in like your name, your password, or other data, credit card details, etc. But you're able to lock it with the key that you've already exchanged. So in transit over the network, it's cryptographically encrypted, so it's just gibberish. It's just it looks like a string of random letters and numbers, and it includes the headers, it includes the body. So all that sensitive data is completely unreadable while it's in transit from your browser to Google server. So, WashU, WashU IT, they can't read your data that's going back and forth between you and Google because it's secured. There's some ways that they can if they inject some SSL stuff. But in general, third parties can't read that data going back and forth. But once it gets to Google server, again, because you've exchanged keys, Google now can unlock that data and they can read it in plain text. So it's a way of securing all of your data while it's in transit. Any questions about HTTPS? Got a couple more things to go over and then we'll be done. So a certificate authority is responsible for issuing the cryptographic certificates to trusted websites. So certificates, they typically cost some money to buy, anywhere from $10 to hundreds of dollars, depending on kind of what certificate authority it is, and there's different levels of them you can get. You may see, like this certificate, it just has a green lock, but you might notice if you go to like a bank website, it has a big green bar. Even try, I'm not sure if my bank has it or not, but like if you go to Yeah, so wait for this to update. Thankfully, I'm not logged in, so you can't see my bank account. But yeah, so here, a lot of large institutions that require a lot of trust, they buy extra expensive security certificates for HTTPS that actually will include the name of the institution right there in the URL bar. So that's just kind of a feature that they use to. It just makes it seem a little bit more trustworthy because you can see right there what the organization is. Usually they'll provide you a little more information too if you click on it. So those are pretty expensive. They cost hundreds or even thousands of dollars. And they usually, to get that kind of a security certificate, it usually involves some paperwork and mailing letters and verifying your identity, because only Charles Schwab & Co. Inc. is able to have that certificate. They've verified. If you're on this schwab.com, you know it's Charles Schwab. So it's very secure, and it's a guarantee that it is that company. No one else can get a SSL certificate for that domain. So again, CAs are typically large, trusted companies. If you just Google, HTTPS certificate, you can find there's quite a few different ones. They work with browser and internet vendors. So usually your computer has a bunch of CA, what are called root certificates installed already. So it can kind of verify trust that way. Your computer knows about these certificate authorities. Let's Encrypt.org is a free certificate authority. They've become popular in the last couple of years. And it's super handy. So if you're building a website and you want to have security, you can use Let's Encrypt. It'll let you do it for free, so it doesn't cost any money, which is really nice. As I mentioned before, HTTPS requires a handshake prior to sending data, where the client and the server kind of exchange cryptographic information. They determine encryption method to use and stuff like that. So this is kind of an overview of that handshake. You don't have to memorize this or anything. So step one, so say I want to make some website, craighuffsiller.com. So I have a server, I've got my website. I have to request a certificate from a certificate authority. So I say, okay, I want a security certificate for Craig or Craigery or craighuffsiller.com or whatever. So the CA will issue the certificate to me that I install on my server. So then when someone on their computer tries to go to craighuffsiller.com, the first thing they do is they request identification. So they make a request, it'll use DNS and end up at my IP, and they say, okay, I want to go to craighuffsiller.com. Can you verify that I'm talking to craighuffsiller.com? So my server will respond with my certificate that I bought from a CA that proves that I am who I say I am, and I respond with my public key. So this is what's called public-private cryptography, like key pair cryptography. If you're interested in it, it's really fascinating how it works. But I send my public key over. The client can verify the certificate. So step 4 is that my client can contact the certificate authority and say, hey, here's the the hash of a certificate or the identifier of a certificate. Is this valid for craighuffsiller.com? Am I really talking to the right person? And the CA can say, yes, that matches our records. You are talking to craighuffsiller.com. So then the client sends, it creates a session key, which is the encryption key that's going to be used, and it can encrypt the session key with the server's public key. So it creates a session key, and then it encrypts it with the server's public key and sends it over. So then the server can decrypt it because it has the private key. Again, this is kind of how that cryptography works. So the server can decrypt that session key, and then it sends an acknowledgement, and now they can talk together using that session key that they've negotiated. So one way to think about it is that the server sends a box with an open lock on it that the server has the key to. The client then puts its own lock inside that box, locks it with the key that the server has, that the client doesn't need the key to, but they can lock it. So they send back this locked box with their open lock in it. Now the server can use their key to unlock that first box and pull out the client's open unlocked box. And it probably also has the key in it. So now the server can put the message in there, close it, lock it with the key they have, send it back. So they've got this shared key now. So that's in a nutshell how it works. It's a little more complicated than that. But essentially it's a way for them to then talk encrypted. We're going to stop here, but I'm going to show you an example real quick of what that handshake looks like using curl. So first I'll show you, again, if you're on a Mac, you can just do this. I don't know if Windows has curl installed by default, but on Mac you can if you're curious. So, and then -v is just a flag, that tells it to be verbose. So if we look for HTTP, WUSTL.edu, so we're just connecting over HTTP, and we'll see what that looks like. So again, it says trying. So it didn't have to, do a DNS request because I've been to WUSTL.edu before, so my computer already knew what the IP was. So it says, trying this IP, connected on port 80 because it's just regular HTTP. Here's the request that I'm sending. So I'm getting, the root on WUSTL.edu. Here's my user agent. Again, it's curl, accepting any type of response. So here's the response now. So first, it's HTTP, but I get a 302 status code, which is that redirect. So it's okay, it's saying, it's moved somehow. Then it gives me a location header. So it says it's moved, but then the location is HTTPS. So this is how they're forcing you to go to HTTPS. They're replying with a 302 on HTTP and redirecting you to HTTPS. Stream offline. Oh, it's back. So the rest of these headers don't really matter because they've sent us this redirect. So now we say, okay, our browser will just automatically do that for us. But if we do curl with HTTPS, and then I'll need to scroll up because there's all kinds of HTML. There we go. See our HTML, so we got a good response. Scrolling back up to the top. Okay, so we've done the curl on HTTPS. Uses the same IP, but now it's connecting on port 443. So now we have to do our HTTPS handshake before we do anything else. So here you can see what that looks like. So first, the client says hello. So my computer says hello to the server, says, hey, I want to, connect via HTTPS. The server responds with a hello. It passes in its certificate. It then passes in the key. So the server says, here's my public key. Then it says, okay, I'm done sending you things. Now the client responds with its key. The client says hello, but encrypted with the server's key.